Hey everybody, Mr. Murray here. I'm Mr. Murray's Math Land. We're continuing on with the approximating area under a curve with trapezoidal sums today, the trapezoidal rule. And we've been using rectangles thus far to approximate left, right, even midpoint rectangles. But today we're going to talk about using a trapezoid and how it's maybe even a better approximation. Eventually the goal is, of course, to find the exact area, but you can't always do that. So we're learning where the approximations came from, where the whole process started. So I'm using actually the same function I used in my Riemann sum video, left and right, just so you can compare and contrast if need be. So we're talking about the area under f of x equals e to the x over the interval 1 to 3. And we're even going to make 4 trapezoids. In that last video, I was making 4 left and right rectangles. So if I were approaching this, from the start, I would be finding my delta x, my difference in x value, and as always, that is the width of the interval, which interval goes from 1 to 3, so 3 minus 1 is a width of 2, and dividing by however many objects you're making. I'm making 4 trapezoids, so I'm going to divide that up, 4 equal spaces, and that gives you 1/2 or 0.5. So again, that is your difference in x values. So here is the, kind of slicing up that region from 1 to 3 into 4 equal regions, 4 equally spaced regions, I should say. That means every 0.5, right? So 1.5, then a 2, then a 2.5. And so the idea is, for this first region, for example, rather than using, say, the left side as the height of a rectangle and definitely being under the curve, or the right side as the height and definitely being over the curve, why not just connect these two and make a trapezoid? And that trapezoid will fit pretty close to that. That's a curve, that's not a straight line, but if I draw a straight line, it's going to pretty closely approximate that curve. So that's the idea of the trapezoidal rule. But you may need just a brief review about the area of a trapezoid. And then we'll see, of course, how you can really take shortcuts with this thing once you get rolling, once you've done a couple of them. So the area of a trapezoid, never forget, I'm sure you remember from geometry, is 1/2 height times base 1 plus base 2. Now a trapezoid has 2 bases, those being the parallel sides, and you probably think of your typical trapezoid as looking like that from geometry. The parallel sides are the bases, and the height is the distance between, that altitude, that perpendicular distance segment between those bases. And that's still, of course, valid, but here your trapezoids are going to be drawn basically on their side. So this is the way we're visualizing these trapezoids in this case. And you can see right here to there. There's that trapezoid. And so the bases are the parallel sides, and those are the vertical segments here. So that's base 1 and that's base 2. And the height is the perpendicular segment that joins those two. That is actually what's kind of on the bottom, right? That is your delta x in this case, is your height of the trapezoids. So okay, so that helps to kind of get that out of the way. And now to get the area of these 4 trapezoids, so T4, 4 traps areas, I'm gonna write it out kind of one at a time, and then we're gonna see how you can really tighten this up and get pretty good with it. So that first trapezoid, that purple one that I've kind of highlighted there, is 1/2. The height is 1/2. So 1/2 of, if you want to write 0.5 or 1/2 of 1/2, times the sum of the bases. Now the sum of the bases is, again, these y values, or these right here, what we were calling the heights for the rectangles, and that is, f of 1 and f of 1.5. That's going to give you the distance there. So f of 1 plus f of 1.5. That's going to be that first trapezoid. And then as I move along to the next trapezoid, between 1.5 and 2, it's still got a width there of 0.5. So that's, the height of the trapezoid. So it's still a 1/2 of 0.5. The bases in this case are f of 1.5. So f of 1.5 gets used twice, notice that, as part of the first trapezoid and as part of the second, plus this, which is f of 2. Maybe you're starting to notice some shortcuts you can take already. The third trapezoid here right? Here's what's the same. It's got the 1/2. It's got the delta x of 0.5. And its two bases, its two vertical segments are f of 2. So again, that f of 2 gets used twice as part of the red trapezoid and the blue one. And the right side of the interval is f of 2.5. Until finally we're here at the last trapezoid. Guess I'll go green on this. And you see where this is headed, of course. One-half of 0.5, and those bases are f of 2.5, the left side of the interval, and f of 3. So unlike the left and the right rectangles, there's each, the left, the right, and everything in between gets used. Nothing gets left out. So that is the long way of writing it out, one at a time. But if they're equally spaced, meaning they have that consistent delta x of 0.5, you could actually shorten this up a lot. And here's the short way to write it, and how I would probably set it up in the future, is to just say, hey, okay, I got my delta x. I know the area of a trapezoid is 1/2 of whatever that delta x is, 0.5, or again, you could do a half of a half and make it 0.25 or 1/4 if you like. And then add up all of the heights. I could factor out the 1/2, the 0.5, and then add up all of the heights. And just notice, here's something that always happens with this trapezoidal rule. The first and the last one, f of 1, f of 3, they get used only once, right? They only belong to one trapezoid, the far left and the far right. But all of the ones in the middle, f of 1.5, f of 2, f of 2.5, they get used twice. So I'm going to really just double that up here and say, hey, f of 1 plus 2, f of 1.5 plus 2, f of 2 plus 2, f of 2.5, until finally I get to the end of the interval and I know f of 3 only gets used once. So I could do this really without the help of a graph, without a diagram. If I really just knew, how wide is my interval? It starts at 1, ends at 3, and getting your delta x. Your delta x tells you the height of each trapezoid, the width, but it also tells you the difference in your x values. So all the middle x values go up by 0.5, and we double those function values because they get used in 2 trapezoids each, except on the ends. And so doing something like this, like with my rectangles, I'm going to use the calculator here, and I'm going to type it in an abbreviated form. I put e to the x in y1 again, so just to be clear there. And so on the outside, 1/2 of 0.5, or if you want to shorten that up and just call it 0.25, and then f of 1, so alpha trace y1 of 1 plus 2 alpha trace. And by the way, you can do these things on like using the table feature if you like to get all those y values and jot them down. I found this works pretty well, but it's certainly not perfect. I know it's a little tedious to type this out. Plus 2 alpha trace y1 of 2 plus 2 alpha trace of y1 of 2.5 until finally I get to the end of the interval, and it only gets used once, so just don't zone out and keep pressing 2 y1. So alpha trace y1 of f of 3, so y1 of 3, and that should be it. Close the whole thing, and we get 17.727 or 728 if you're rounding or truncating. So 17.728. That's my approximation for the area. And so that's how you do a trapezoidal sum. And that's that, although it's nice to kind of look now and say, when we were doing these before with the rectangles, we clearly knew the left was under this function, and we clearly knew the right Riemann sum was over an overestimate. And that's because the function was increasing. Anytime you're increasing, your left is going to be under, your right's going to be over, because you're always grabbing a shorter or a higher value. But what about the trapezoids? It might be tough for you to see or visualize. Is this approximation that I got? It's pretty good, it's pretty close, but it's not perfect. Is it slightly more or slightly less than the actual area? And that actually has to do with concavity. And in this case, because I'm concave up, and it wouldn't really matter if I was concave up and decreasing or concave up and increasing, but anytime you draw a trapezoid on a concave up region, and I'll just exaggerate it by grabbing 2 points there, if you connect those, because you're concave up, your curve is sort of, sagging below there like that, your trapezoid is always going to be above a concave up region. So this I know is slightly more than the actual area. And it's just easier to see the way I drew it. But of course, if you take a region like that and do that, you are slightly over the curve. So anyway, we'll talk more about that as we go on, but that's how you do a trapezoidal one. Hopefully that made sense, and you're off and running with these. Got any questions? Just let me know.